a 380 volts AC 5-wire system, the neutral leg typically does not require a fuse. The primary reason is that the neutral conductor is already protected by the overcurrent protection devices, such as fuses or circuit breakers, installed on the phase conductors. These devices are designed to interrupt the circuit if the current exceeds a predetermined value, safeguarding the entire system, including the neutral conductor. If an overcurrent situation arises on any of the phase conductors, the corresponding overcurrent protection device will trip, effectively cutting off the power supply and preventing damage to the system. This protection extends to the neutral conductor because any imbalance in the phase currents will inevitably result in current flow through the neutral. Another crucial aspect of neutral protection is the grounding system. In most electrical installations, the neutral conductor is bonded to ground at the main electrical distribution panel. This bonding creates a low impedance path for fault currents to flow back to the source. If a short circuit or ground fault occurs, the fault current will rapidly increase, triggering the overcurrent protection devices to trip and clear the fault. This grounding system provides an additional layer of safety by ensuring that any abnormal current flow is quickly detected and interrupted, preventing potential hazards such as electrical shock or a fire. Installing a fuse on the neutral leg would therefore be considered redundant. Firstly, the existing overcurrent protection devices on the phase conductors already provide adequate protection for the neutral conductor. Secondly, the grounding system further enhances safety by providing a low impedance path for fault currents. Thirdly, adding a fuse to the neutral leg could potentially introduce new safety risks. If the neutral fuse were to blow, it could interrupt the return path for the current, leading to voltage imbalances and potentially damaging equipment. In a 380 volts AC 5-wire system, the voltage between any phase and neutral is typically 220 volts AC. This voltage is commonly used for powering single-phase loads such as lighting and small appliances. The 380 volts AC voltage is used for three-phase loads such as motors and heating elements. 5 wires in the system are three-phase conductors, a neutral conductor, and a ground conductor. The ground conductor is typically connected to the neutral conductor at the main electrical panel. This connection provides a low impedance path for fault currents to flow back to the source. The overcurrent protection devices in the system are designed to protect the conductors from overload and short-circuit conditions. These devices are typically fuses or circuit breakers. Fuses are one-time use devices that melt when the current exceeds the rated value. Circuit breakers are reusable devices that trip when the current exceeds the rated value. The National Electrical Code, or NEC, provides guidelines for the installation and protection of electrical systems. The NEC requires that all conductors be protected from overcurrent. The NEC also requires that the neutral conductor be grounded. The NEC does not require that the neutral conductor be fused in a 380 volts AC 5-wire system. However, some local jurisdictions may have additional requirements. It is important to consult with a qualified electrician to ensure that the electrical system is installed and protected in accordance with all applicable codes and regulations. The absence of a fuse on the neutral does not compromise safety, but instead relies on a comprehensive system of overcurrent protection and grounding to ensure the safe and reliable operation of the electrical system. The operation of a 380 volts AC 5-wire system involves several key components working in concert. Firstly, the power source, typically a utility transformer, provides the 380 volts AC 3-phase power. Secondly, the distribution panel receives the power from the source and distributes it to various circuits throughout the building or facility. Thirdly, the branch circuits carry the power from the distribution panel to the individual loads such as lighting fixtures, appliances, and equipment. Fourthly, the neutral conductor provides a return path for the current from the loads back to the source. Fifthly, the ground conductor provides a safety path for fault currents, protecting against electrical shock. The overcurrent protection devices, such as fuses and circuit breakers, are installed in the branch circuits to protect the conductors and equipment from overloads and short circuits. These devices are carefully selected to match the current carrying capacity of the conductors and the rating of the equipment. When an overcurrent occurs, the protection device will trip, interrupting the circuit and preventing damage. The grounding system is essential for safety. It ensures that any fault currents will flow back to the source through a low impedance path, tripping the overcurrent protection devices and clearing the fault. Without a proper grounding system, fault currents could flow through unintended paths such as the building structure or equipment housings, posing a serious risk of electrical shock. The NEC provides detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the location of ground connections, and the bonding of metal enclosures. These requirements are designed to minimize the risk of electrical shock and fire. In summary, the 380 volts AC 5-wire system is a robust and reliable power distribution system that relies on a combination of overcurrent protection, grounding, and proper installation practices to ensure safety and performance. The absence of a fuse on the neutral conductor is not a safety concern, as long as the system is properly designed and installed in accordance with the NEC and other applicable codes and regulations. The 380 volts AC 5-wire system is a common configuration for power distribution in many industrial and commercial settings. Understanding its operation and safety features is crucial for electricians, engineers, and other professionals who work with electrical systems. Furthermore, it is important to note that while fusing the neutral conductor is generally not required or recommended, there may be specific situations where it could be considered. For example, in certain sensitive electronic equipment, a fuse on the neutral could provide additional protection against voltage imbalances or other anomalies. However, such applications are rare and would require careful evaluation and engineering analysis. The decision to fuse the neutral should be based on a thorough understanding of the specific requirements of the equipment and the overall electrical system. It is also important to consult with the equipment manufacturer and a qualified electrician to ensure that any modifications to the system are safe and compliant with applicable codes and regulations. The selection of overcurrent protection devices is a critical aspect of electrical system design. The devices must be properly sized to protect the conductors and equipment from overloads and short circuits, while also allowing for normal operating currents. The NEC provides detailed guidelines for selecting overcurrent protection devices, including ampacity tables for conductors, dirting factors for ambient temperature and conductor bundling, and interrupting ratings for circuit breakers and fuses. The interrupting rating of an overcurrent protection device is the maximum fault current that the device can safely interrupt without failing. It is important to select devices with an interrupting rating that is equal to or greater than the available fault current at the point of installation. Failure to do so could result in the device failing to clear the fault, potentially leading to equipment damage or personal injury. In addition to overcurrent protection, surge protection is another important aspect of electrical system design. Surges are transient overvoltages that can damage sensitive electronic equipment. They can be caused by lightning strikes, utility switching, or other events. Surge protection devices, or SPDs, are designed to divert surge currents away from the equipment, protecting it from damage. SPD are typically installed at the main electrical panel and at individual equipment locations. The NEC provides requirements for the installation and coordination of SPD. The neutral conductor in a 380 volts AC 5-wire system plays a vital role in ensuring the proper operation of single-phase loads. As mentioned earlier, the voltage between any phase and neutral is typically 220 volts AC, which is commonly used for powering lighting, appliances, and other single-phase equipment. The neutral conductor provides a return path for the current from these loads back to the source. If the neutral conductor is not properly sized or connected, it can lead to voltage imbalances and other problems. Voltage imbalances can cause equipment to overheat, malfunction, or fail prematurely. The NEC provides requirements for the sizing of the neutral conductor to ensure that it can safely carry the expected neutral current. The neutral current is the sum of the unbalanced currents from the phase conductors. In a balanced three-phase system, the neutral current is zero. However, in most real-world systems, the loads are not perfectly balanced, resulting in some neutral current. The NEC allows for the neutral conductor to be sized smaller than the phase conductors in certain situations, such as when the majority of the loads are non-linear. Non-linear loads, such as electronic equipment with switching power supplies, can generate harmonic currents that flow in the neutral conductor. These harmonic currents can increase the neutral current, requiring a larger neutral conductor to be used. In addition to sizing, the proper connection of the neutral conductor is also critical. The neutral conductor must be securely connected to the neutral busbar in the main electrical panel. The neutral busbar must be properly grounded to provide a low impedance path for fault currents. Loose or corroded neutral connections can cause voltage drops and other problems. These problems can be difficult to diagnose and can lead to equipment damage or safety hazards. Regular inspection and maintenance of electrical connections are essential for ensuring the safe and reliable operation of the electrical system. The NEC provides guidelines for the inspection and testing of electrical systems. These guidelines include visual inspections, insulation resistance testing, and ground impedance testing. Regular testing can help identify potential problems before they become serious. Furthermore, it is crucial to understand the specific requirements of the local electrical codes and regulations. These codes may vary from jurisdiction to jurisdiction and may have additional requirements beyond those specified in the NEC. It is always best to consult with a qualified electrician or electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and regulations. In conclusion, the decision of whether or not to fuse the neutral conductor in a 380-volt AC 5-wire system is a complex one that depends on a variety of factors. While fusing the neutral is generally not required or recommended, there may be specific situations where it could be considered. The most important thing is to ensure that the electrical system is properly designed, installed, and maintained in accordance with all applicable codes and regulations. This will ensure the safe and reliable operation of the system and protect against potential hazards. The overall safety and performance of a 380-volt AC 5-wire system hinge on a comprehensive approach that encompasses not only the absence of neutral fusing, but also the correct implementation of overcurrent protection, grounding, conductor sizing, and adherence to relevant electrical codes. Ignoring any one of these aspects can compromise the system's integrity and increase the risk of electrical hazards. Electrical systems need regularly scheduled checkups. It is the responsibility of the owner and those using the electrical systems to keep things running smoothly.